Okay, so this is going to be an overview of the Kraken monophosphine library, which was published a couple of years ago. Essentially, what I'm going to do is at the start, I'm going to contextualize the use of phosphine ligands in organometallic chemistry. I'm going to talk about how these phosphines have been historically featurized, and then how these ligands are featurized within Kraken. Then we're going to talk about a couple of case studies which have used Kraken over the last few years. And at the end, I'm going to show you how you can access this resource through the website from Mulsi. So to start, phosphines are some of the most widely used ligands in homogeneous catalysis. And there are a number of examples where these are used and where the ligand effects have a demonstrable effect on catalysis. This is an example where with oxidative addition, so this is a palladium dot complex undergoing oxidative addition with an aryl halide, and then the authors changed these different R groups on this triphenylphosphine scaffold, and they found that increasing the electron withdrawing groups as the R groups increases the rate of oxidative addition. There's also another piece of work here in Dalton Trans 2014 where they showed looking at different rates of oxidative addition. You can go through mono versus bis ligated oxidative addition pathways, and that's all to do with the ligand that you put in. Kind of over the last 20 or so years, there's been a whole bunch of these different what we call designer phosphine ligands. And this is one particular example of these biaryl monophosphine ligands, or called Buchwald ligands, where you can change a whole different number of substituents across this ligand scaffold to give you different reactivity. And this is one example here. So this is the Buchwald-Harwick amination reaction, where you can choose between primary and secondary alkylamines to react with an aryl halide. And so you'd use this Brett-Phos if you want to use a primary amine, or Rufos if you wanted to use a secondary amine. These ligands could also be used to induct asymmetry within the molecules. This is a hydroviolation reaction with ethylene here and nickel, where this ligand, which has chiral groups appended on this phosphocycle, can be used to get products like this in up to 91% EE. And also phosphorus is chiral itself. And so this family of ligands, which is normally called the bidyne family of ligands, where we're using the phosphorus here as the point of chirality, and you can get induction like this up to 97% E with this type of ligand. So it's clear that these ligands have demonstrable effects on the reactivity, and people since the 1970s have tried to featurize these different ligands. So like everything else in chemistry, the effect of phosphine is determined by a mixture of electronic and steric effects, where the electronics of these R groups bound to the phosphorus can affect the donation ability, for example, on the phosphorus. And also, obviously, the size of the groups on phosphorus will affect the overall size of the ligand. And Tolman was one of the first people who looked at this in terms of parameterizing ligands and came up with a couple of different descriptors which map the electronic and the steric effect. So this first one looks at the electronic effect, which is the Tolman electronic parameter, where we have a phosphine bound to a nickel tricarbonyl species. And the electronics from these R groups affect the carbon monoxide A1 stretch in the IR spectrum, and this can be used to correlate electronic effects. In terms of the size, we have this cone angle, where we have an atom placed at 2.2 angstroms away from the phosphorus center, and then look at the furthest points in the van der Waals radii here, and then the angle which goes between the two is known as the Tolman cone angle. So there are a couple of issues with using these descriptors, although they do work in a variety of number of cases. So the Tolman electronic parameter involves often making the nickel carbonyl complexes or the manganese carbonyl complexes, which are fairly unpleasant, and also going to measure the IR spectrum. And there are a number of examples where this cone angle insufficiently describes the steric environment on the phosphorus center. So people are trying to come up with these modern molecular features, which are in most part derived from DFT calculations, to try and supplement and give a better description of the phosphorus electronics and sterics. So these are a couple of earlier examples, couple of which are still used today in Kraken and other databases. We have this Vmin, which is the minimum electrostatic potential on the phosphorus lone pair, and this was shown to quite nicely correlate to the Tom electronic descriptor. And then we have this buried volume term, which in a number of simple phosphine cases was shown to correlate with the cone angle. So we have these two new descriptors which can be calculated from DFT calculations, and to avoid having to make these complexes. And since this, there's a whole bunch of other different descriptors which can be used to describe phosphine. So we have MBO charges, NMR chemical shifts, things which describe the homo-lumo, things dispersion, sterimol, and parameterization and solvent accessible surface area can be used to describe these phosphines, all of which are used in Kraken. And there's one final point, which you can't always pick up by experiment, but in many cases, monophosphines have a number of different conformations. And so you can calculate these different conformations and calculate the descriptors related to these conformations. And you can end up getting this conformational weighting. So mathematical minimum and maximum values, descriptors, as well as Boltzmann averages in a conformational ensemble. So the Kraken monophosphine library attempts to use all these different molecular features for phosphine ligands for about 1,500 different compounds. And there's also a virtual library of Kraken ligands, which puts up to about 191 million. I'm not going to talk about this today because of the time, but these are calculated using ML predictions based on the ones that are calculated as part of the normal library. So again, we're incorporating conformational ensembles here, calculating descriptors, and then we can represent this descriptor space in a number of different ways, which I'll talk about in the next few slides. So as a quick overview to how these ligands are calculated. So start off with the ligand SMILE string, and this undergoes a 3D conversion where we generate the nickel tricarbonyl species. This was directly inspired from Tolman's early work, and also the free ligand. These undergo then a geometry optimization using XTB before putting into the CREST program for a conformational search. This conformational search is performed on both the nickel complex and the free ligand. And then for both of these things, the XTB properties are calculated. From these two complex and free ligand ensembles, a bunch of conformers are selected for DFT. And so they've selected based on these two criteria. The first criterion is that the conformers which minimize or maximize a whole bunch of different XTB level steric descriptors. And then secondly, if that up to 20 conformers in total within a 3 kcal per mole energy range. And if it's more than that in the free ligand conformer set, a selection is made by pruning the conformers down using an RMSD. And the purpose of this is so we can get a structurally diverse array of conformers for calculation using DFT. This is done just on the free ligands. So all the complexes which were nickel bound, nickel's taken off, and so we just have free ligands for this. And then we undergo joint optimization and then a single point energy calculation. And all of these steps are streamlined in one calculation. And then from this, we can then calculate DFT properties. If you want more information on how these are collected, this page on the MolC website is a brief overview of this, or you can go to the supporting information of the original Kraken publication for a detailed overview on that. There are about 190 total descriptors, both steric and electronic, in Kraken, and so getting to visualize this is pretty tricky. And so we end up using these dimensionality reduction techniques. So I'm just going to show you principal component analysis, where we have 4 principal components, which represent a 63% of the total variance in the descriptor library. And we can pick out what each of these principal components mean. So principal component 1 is related to the volume-based descriptors. Principal component 2 is related to the parameterization. Principal component 3 is to do with the flexibility, and principal component 4 is to do with the orbitals. Now, because a lot of these descriptors within Kraken are mainly steric based, if you want to differentiate nicely between electronic and steric features in a ligand, one helpful approach is using what we call the modern Tolman map. As I mentioned before, we have this V min term, which is collinear with the Tolman electronic parameter. And then we have this V ver term, which is correlated with the Tolman cone angle. And what we now have is a map which is purely electronics on the x-axis and sterics on the y. So one of the examples of how we can use this space, and this is to kind of design what we call a universal training set of phosphine ligands. So in this paper in 2022, universal training set of 32 monophosphine ligands. 32 was selected because that's a third of a 96 well plate. And these selection of ligands were designed for the purpose of cross-coupling chemistry, so things like Suzuki-Mara cross-couplings and Buckwood-Hartwig aminations. And the idea behind this was, if you have a representation of the phosphine descriptor space, which is here, and we have a hotspot of reactivity, how one might go about finding that hotspot of reactivity is where this approach really kind of does really well. And so what you might do using a biased ligand selection based on literature or chemical intuition is select a whole different selection of ligands over the principal component space, but what you end up doing is end up missing the hotspot entirely. However, if we select ligands systematically across the principal component space, we can end up getting a wide selection of ligands across the whole space where we can find our hotspot hopefully relatively quickly in comparison to the conventional approach. So how this works in practice is we take the Kraken PC space and we filter down for commercially available ligands. And then this space is then clustered using k-means clusters. We choose 32 here for each of our 32 ligands that we want to select. We then take the ligand which is closest to the center of this cluster for testing, and you can see now we kind of span a wide range of ligand space. And as I reiterate at the point that this approach allows you to give a good sweep over different phosphine properties across the whole space, and hopefully you're allowed to find your hotspot or hotspots of reactivity quicker. So I'm going to move on to a couple of case studies now. So this is the first case study on this enantiodivergent palladium catalyzed CC bond formation from 2018, where we take this trifluoroborate, which is an anti-air enriched, undergo an oxidative addition, and this can either undergo stereo retention or stereo inversion. And the initial part of this looked at a whole range of ligands and their overall size. So we're using the size to measure, using solid angle here to measure the size. And this can be compared to the cone angle. And there isn't really a clear relationship between the solid angle and the EE, where we have inversion as a minus and retention as a plus. So we kind of go to our descriptor library where we can generate multivariate linear regression models. So this is one of the models which was generated to describe the reactivity of this, and has these 4 components which describe a significant part of the mechanism. And so this PC anti-bonding relates to the back bonding of the phosphine. And so going looking at this transition state, this back bonding would favor this kind of formation where we have stereo retention. We also look at the lone pair. So this is the V min term I mentioned a few slides ago, which is related to the sigma donation for the phosphorus to the palladium. And this form favors this transition state where our boron and palladium on opposite sides, we end up with a stereo inversion. And then the steric terms here, which are these two stereomole terms. So this B1 minimum width depicted here, and this L term, which is the overall length here from the phosphorus center. Tells you about how the complex undergoes reductive elimination or beta hydride elimination. And from this, you can remove ligands which are too large and they undergo beta hydride elimination. You can simplify the model down to this two-component model, which just describes the transmetallation in the reaction. The second case study is using Kraken descriptors in the context of univariate classification to look at phosphine ligation state. I mentioned before at the start that people have shown the difference in oxidative addition kinetics and speciation due to ligand effects, and we see the same thing here play out within catalysis. So taking these two examples of nickel catalysis, these two cross-coupling reactions, which have 34 and 90 monophosphine ligands respectively, all this data was combined for these different types of reaction, and looking at this, see if any relationship be found with the overall yield of the reaction. So these are three reactions which fit into the two types I showed you on the previous slide, and what we're doing is plotting descriptors here on the x-axis and the yield of the reaction on the y. And if you look at cone angle, there isn't really a good correlation between the yield and the cone angle at all. We know that the varied volume term is, in some cases, collinear to the cone angle, in simple cases at least. And you can start to see a reactivity cliff emerge, where beyond a certain value for the varied volume, the reactivity or the yield rather goes down to 0%. And if we end up using the minimum varied volume here, where most of the ligand R groups are outside this sphere, we do see a nice classification where we set the Y threshold here at 15% yield, which is the number of turnovers. We see this clear cut. So what does this mean in terms of ligand speciation? And so a bunch of different spectroscopic studies were done, mixed nickel cod, two ligands and reacting with this aldehyde, and you can either form this species here with two phosphines ligated, or this species here with one phosphine ligated. And again, we're moving down from cone angle, and then our varied volume Boltzmann average. You can see there's not really a clear trend. However, when you go to this minimum varied volume turn, you can see a clear reactivity cliff between the ligation state of 2, so a complex which looks like this, and ligation state of 1, and a complex which looks like this. And this can be directly related back to these yield cutoffs. And so in these cases where we have ligands which have a high yield, they have a certain ligation state. And then a whole bunch of different reactions were then looked at in the context of nickel and palladium catalysis, where reactions were rendered active, predominantly in the nickel sense in L2, and then palladium were rendered active as L1. So I was going to finish on by talking about the Kraken website, which was developed with Molsey. So this is a place where all the information on Kraken can be found, and there's a few other different features I'll hopefully go through. So just a quick overview. There's an interactive view map space, so you can see this is another way of representing the phosphine ligand space. You can see how all these are close to each other in space. You can do a substructure search to find the ligand that you want, and this you can use a smile string, or you can draw the structure. There's functionality where you can view and download the descriptors that you want for the ligand that you're interested in. And there's also this PCA neighbor search, which can be used, which relates back to the PHOS universal training set I mentioned a few slides ago, and where if you know you have a ligand which works well in a given particular area of space, you can find the ligand which is closest to it, and it should have similar properties to it. So what I'm going to try and do now is I have the Kraken, hopefully you can see the Kraken website. I'm going to try and give you a quick overview of how this works in practice. And so this is the main page. There's a few different statistics on it in terms of number of ligands and conformers and etc. And then if you scroll down, we get to this interactive UMAP space. And so what you can do is you can hover over this and see all the different phosphine ligand structures. This on the left, on the right-hand side, you can filter down to the what you're interested in. So, for example, if I want to take out phosphines with 3 carbons attached, just click the button there, and they disappear. And if I'm in, look at the interesting ligands I want to look at in particular. Let's say this one. We click a button here, and it loads a new page for us, and we get some information. So here's the structure again. We have a smile string and various different inchy representations, our molecular weight. And we have a table up on the top right, where we have a whole bunch of different descriptors, which I mentioned to you before. These are all DFT descriptors, but if you want to have a look at other descriptors, like the ones derived from the ML models, which I briefly mentioned at the start, or the XTB ones, you can do that. And they're loaded here. And you can download these as a CSV file for use in whatever purpose you have, like modeling, for example. Down the bottom here, we have a 3D representation of the phosphine ligand, and then a list of all the conformers that are loaded into the system, so you can see how these ligands change as a function of conformer. And then this bottom bit here is where this ligand ends up in space, so they're represented by this red triangle. This is UMAP space. We can change this to PCA space if we want to, and then you can see what ligands are nearby. So let's quick go over the search feature. And so we can search using a SMILES or a smart string, which is what's shown here. And so you can see all these ones with phosphorus carbon double bonds are shown. But we can also open up this sketcher. And so if I just want to find something with a benzene ring in, I'll put the benzene ring here, and then we'd end up getting all the different ligands with aromatics, which would put all the benzenes in. We have this nice neighbor function, which looks at ligands and structures. So we don't have to go through the main page. So I happen to know that triphenylphosphine is ligand number 17 in the library. We can search for that. And then we can see the space which surrounds it, but we can also see a list of all the different ligands which are close to triphenylphosphine in the ligand space. And information on how these ligands are calculated is given on the library details. And this is in the process of, the website is in the process of being updated gradually, but we're pretty happy with what we've got so far. And I'll leave it there, Olaf, unless someone has any questions.
All right, questions by the audience.
Hi, can you hear me?
Yep.
So for one of the slides at the very beginning, I remember there is a clustering, and for different PC clusters, you labeled it like volume and parameterization and other features.
This one
how
here.
do you decide? Yes, how did you decide like which PC is which characterization?
Can you say that once more?
How do you decide like the PC1 is volume?
Oh, I see.
Yeah.
So each of these principal components is a linear combination of all 190 odd, or actually in this case, because we trim it down to 130 descriptors. And so you can look at the weightings of the coefficients in that linear combination. And if you look at the top 10 descriptors in PC1, PC2, PC3, the ones which come out the most are volume descriptors. So these are the ones which contribute the most to principal component 1. And the same thing is the case with principal component 2, where most of the terms in the top 10 of the descriptors which contribute to principal component 2 are related to parameterization.
Okay, I understand. Okay, thank you.
Great.
More questions? All right, then let me finish the recording.